Hello, everybody. Thank you so much for joining us in our April webinar. So today we have Chenyu Yu, who is an assistant professor in the Department of Applied Mathematics and Statistics and Computer Science at Stony Brook University. His research focuses on generalization and making machine learning models more reliable, with applications in healthcare, biomedical imaging, and cognitive neuroscience. He received his PhD from Yale University in 2024 under advisement of James Duncan, his master's from Stanford under Daniel Rubin, and did his undergrad at RPI in electrical engineering. He has also spent some time at Facebook AI Research and Google Research. Chenyu has received many important awards for his work, including the AAAI 2026 New Faculty Highlights Award and the ICML 2025 Oral Presentation Award. He currently serves as an associate editor for multiple journals, including IEEE TMI, for which he recently won the Distinguished Associate Editor certificate, and also Medical Image Analysis. So we have a very packed talk today with a lot of content. So I will give the floor to you, Chenyu.
Thank you. Thank you for the kind introductions. I'm very glad to be here. So, today I would like to, very excited to tell you about my work, how to make the biomedical machine learning system, more robust. So first of all, I would like to talk about why we need the machine learning for the biomedical image analysis. So the first reason is turns out they have a lot of diagnosis errors in the radiologies, which cause a lot of patient deaths. The second reason is also pretty important for me because two-thirds of world population is hardly to access to the medical imaging or radiologists. Currently, they are dying some things of the TBs of lung cancers because they are hardly to find the radiologists to look at their CT scans or X-rays. So that's over 4 billion people we can potentially using the machine learning algorithm to relieve these kind of issues. That's what we are trying to focus on. So today's machine learning systems are widely deployed and deeply embedded into the different kind of the biomedical applications. So here I would like to take the biomedical imaging segmentation as examples because there are so many real-world applications in the real clinical situations. So first of all, they can be using for the hospital for the diagnosis, or they can using for the clinical trial for the early warning or treatment recommendation, or they can using for the surgery interventions or the radiation therapies. So this kind of the biomedical machine learning system are out there and touch millions lives every day. On one hand, it's really exciting because there are so many potential across in the different kind of the biomedical application. But on the other hand, it's also extremely risky because this kind of system may fail. They are trying somehow they will make inaccurate diagnosis or treatment in some extremely scenario, and the consequences of their failure will be magnified by their reach. So let me give guys some examples. So the first challenge is that the model may fail when they are trying to deploy into the insufficient label scenario. So as we can see on the graph on the right, so we can see that the amount of label data required to building this kind of the state-of-art biomedical model is grow up exponentially over the time. So somehow the popular word is kind of like the scaling laws. So however, especially for the medical domains, the red line shows the number of only available labels has only grow up linearly or even less. So nowadays, the data is new oil. There is no better tagline to describe culinary revolutions. So all the projects you are trying to working on or look at, so you need a lot and a lot accurate labeled data. This may not be a big problem for the computer vision domains because they already have a very large annotated training sets such as ImageNet. But for the medical domains, it's not easy to get this kind of their high quality annotation due to some privacy concerns and security restrictions. In addition, manually label this kind of the medical data demands high expertise and also is time consuming. So this indicates insufficient label scenario is a serious bottleneck to creating or building this kind of robust and reliable biomedical system. Therefore, we need better solutions. And in the first chapter, I will discuss how to address these kind of problems. The second challenge is that the model may fail in the imbalanced class distribution. So here we can see that the class imbalance problem refers to the situation where the number of the available labels, like the pixel or voxels, belong to one class, will significantly outnumbers the voxels from the other classes. So for example, like in the medical image domains, the underlying class distribution is naturally imbalanced. So here's a quick examples, and also it's very important for the medical image analysis task because they are somehow are quite different from the general image analysis task. So on the left, we can see the thumbnails of the kitten is a great example because we can see the majority pixels in the images telling you there is a kitten sitting there. So the segmentation task for the general image analysis task may be not very difficult because majority pixels showing the signs there of a small kitten there. But on the right, we can see there are only small portions of the voxels telling you there is some lesion regions or tumor regions which marking the green color here. So um, so we can see that there are only small portion of these kind of images telling you this very important findings that you need to segment. So this will lead the model to perform well on the average or the majority classes, but they will perform poorly on the minority classes. To address this kind of problems, we need to optimizing the model to do well in all the classes. And also we will, in the second chapter, I will telling you how we can substantially reduce the disparities between the majority classes and the minority classes. So the third challenge is that the model may fail in some diverse distribution. So here are some examples of the diverse biomedical data distribution, including the CTs, MR, or PET, or different kind of the imaging modality. Also, they including the different kind of the anatomical regions. And also, it's very challenging to make the model to perform well on the diverse biomedical data. In other words, we need to address the distribution shift problems because this will lead the model to become unreliable in the diagnosis. So here's a very let me give you guys a real world examples. So the health company Epic using the machine learning company algorithm to generate the early warning for the patient at the risk of the symphysis disease. So this kind of disease has already caused one third of deaths in the United States hospitals. So here is Epic did. He trained the model on the patient from three hospitals and direct show it works and then deploying to the hundreds of the other hospitals. So because the clinical environment is keeping changing, they may have different kind of the protocols or the equipment. So the shift problems, data distribution shift problems is very obvious at every wells. So in the new environment, it turns out the model misclassified the symphysis most of the time. It's very shocking because this kind of model have already deployed into the 100 hospitals. So the question here is how we can address the distribution shift problem or thinking broadly. Can we really building the model that can generalizing well across in the diverse biomedical data? So here's the overview of my current research. Each project reflects a different aspect to making the biomedical machine learning system more robust. So concretely, I'm going to talk about how we can optimizing the existing model by finding the right inductive bias in the very insufficient label scenario. And then I will going to talk about how we can train the model become more robust across in the different kind of contributions. And further, I'm going to talk about how we can build in the general method on the real world distribution scenario. So, and then I'm trying to deploy them into the real world clinical applications. So underlying this kind of work, my general overall research goal is trying to making the biomedical machine learning system more robust in the real world application and trying to develop the reliable method that anchor to the insufficient label scenario and imbalanced class distributions. And further, because the biomedical imaging is quite large and complex, so I'm trying to simplify the training process, can enjoy the benefits, enable the method to enjoy the benefits such as sample efficient, reduce variance, and faster training conversions. And then trying to formulate in the way to have the general method across in the diverse biomedical data. And we will see this talk through today's presentations. So I will start the idea to finding the right embedded bias from the imperfect medical data. So one of the motivation is coming from the once there is only small portion of data have been annotated, and also it's not easy to create the ground truth labels. So so for my research in the medical schools, for example, like I have over 3,000 3D scans, including a CT, MR, imaging modalities, but there are only 50 scans have ground truth labels. It's a very serious problem because imagine that we are trying to train with the insufficient label scenario. It's very challenging to making the reliable biomedical system, and it will lead the model to make inaccurate diagnosis and unreliable treatment recommendations. How we can really making the system more reliable across in the insufficient label scenario. So as a popular approach, contrast learning proof is a good approach or useful approach to learn a good representation from the unlabeled data. So what's the contrast learning? The basic idea here is pretty simple. We are trying to put the semantically neighbors together and push apart the non-neighbors. So for example, we want to learn a representation from the cartoon character. We want the green cat as close as to the yellow cat and pull away the cows from this kind of yellow cat. So by doing this, we can find the good representation or find the right embedded bias by the contrast learning. So here we can try to formulate the problem as how can we really learn a good representation without using any labels? So our key methodology is trying to find the right embedded bias by the contrast learning. So here's the in the prior work in the computer vision domains, they are trying to apply the standard pixel level constraint to measure the two predictions from the F1 and F2s on the unlabeled training data. So, however, it's not enough to find the right data bias, especially in the medical imaging domains, because there are overlooked some anatomical structures. So let me give you guys some examples. So as we can see there on the left is one of the project I was did in Google research. So here actually we are trying to reconstruct the neuron circuits, and here we can see the downside some 3D space is telling us the anatomical structure is actually the key factor to help us to identify the right neurons. So to this end, we can consider to incorporating some geometry information as a writing database. So in the following, I'm going to talk about how we can formulate this kind of idea on the unlabeled training data. So the natural way to do this is trying to using the sign distance functions, which are around the numerical analysis of surface and shapes since 90s. So this kind of function will give us a very smooth representation, also preserve some real positional information, which can indicate whether the voxel was inside or outside the surface, and to help us to find the right database. So more concretely, given the 3D volumes, we can calculate the boundary representation and using the sign distance functions, and then we can further to quantify the decision boundary of the surface. And the sign will be indicate whether the pixel or voxels was inside or outside the surface. So by doing so, we can get some geometry knowledge from the unlabeled medical data. And the follow-up questions is how we can incorporating this kind of knowledge into the training pipelines. So unlike the prior work, like the pixel level constraint to measure the predictions from the F1 and F2s, here we enable the model to coherently to generate the prediction and assign these functions. And further, we can combine them together, apply the two separate dropout masks, and compare them as the positive pairs through the contrast learning pipelines. And also, we don't want the representation become degenerated, so we add a different kind of the anatomical view from a different kind of location, but still within the same patient to learn the good representations. So empirically, we show that our method compared to the standard training pipelines, and here the 10% training data refers that we only during the training we only using the 10% training data have high quality annotation. The remaining do not have any high quality annotations. So we evaluate our method on the several benchmark data sets. Here we take the left entrance and penetrance data sets as examples. So we can see that our proposed method can significantly improving the segmentation quality in terms of the dice scores and the ASD matrix with a very small portions of the high quality label cost. In empirical qualitatively, we also see that our proposed method can better to capture the boundary regions compared to the other competitive algorithm. So here we can say that we somehow achieved a good result in the 10% label ratios, but it's not perfect yet. So in the follow-up questions is that we are trying to deploy this kind of the machine learning system in the real clinical situations. We want to take a step further to ask whether we can build in the system more reliable and robust using the much fewer label cost. So in the following, I'm going to talk about how we can address these kind of problems. Okay. So the motivation is actually coming from the fact that the medical imaging is naturally reconstructed in the 3D space. So here we can take the left entrance as examples. All the thing we can saw here is only the projection, whatever exists in the physics. We cannot see the exactly 3D shapes. We only see some projections of the 3D images. They are noisy and or incomplete, but they are highly correlated. And also the idea of the multi-view contrast learning is kind of like you want to flip these kind of things around. You want to learn the representation where the single anatomical projections will mapping to the same data point, and we don't want to be invariant into the projections. So here the key in database, I think, make everything works is that the way you measure do not change the word itself. There are some physics things out there. No matter how you can measure these kinds of 3D volumes, the underlying biomedical semantics will not change itself. So by doing so, we can another thing we can do here is why not we to take different kind of views to look at this kind of 3D medical imagings. They should be agree upon the same underlying biomedical semantics. So we add more projections from different constants for the better discriminations. So uh, we can see that our the learned representation quality can getting better under the much more challenging limited annotation scenario. So for example, like the 1% label ratio here. So let me quickly wrap up this kind of sections and how to find the right database is a core point to enable a lot of explorations in the biomedical domains. So as a follow-up project, we are trying to explore the dynamics that take place in the voxel-wise contrast learning to elevate the concern of the dimensional collapse. And further, we are trying to explore the transformer architecture to find the right database and underscore the significance of the attention mechanism can serve as a powerful tool for better understand how the model work internally to learn this kind of the anatomical structure. And also the follow-up work is trying to incorporating the self-supervised learning and diffusion models to find the right database. And coherently, we are trying to find the right database between the medical imaging and the medical text data. And more broadly, there are tons of other the work in our community trying to extending of our taking our idea in the different kind of the directions and apply to the different kind of the problem. So here is some representative work using our contrast learning framework to building more robust segmentation algorithm or apply to the different kind of the biomedical applications. So in the first chapter, we talk about how to find the right database. So in the following, I'm going to talk about how we can train the model become more reliable and robust against the different kind of the cloud distribution shift problems. So going back to the motivations, so it's very big challenge for the medical imaging analysis. The reason is in the medical domains, the model may perform well on the majority of classes or the average, but they somehow will struggle about the minority group or the regions. But this kind of region is actually very important for the diagnosis. For example, like the lesion regions or the tumor regions or other kind of the disease region. Most of them are belong to the minority classes. So the reason we think is that the model may suffer this kind of risk is because we are trying to using the standard training pipelines. For example, like using the standard training objective, we are trying because we are trying to minimizing the average training loss across in all the available training voxels. So which will lead to the poor performance in the minority classes that we actually care about. So let me give you guys some examples. So trained with this kind of imbalanced class distribution, the model may generate the blurry contour or misclassify some minority classes. As we can see from the left side examples, the model is misclassify some real tumor regions that's actually marking the green color here. And also in the same time, the model may suffer the risk of the model collapse issues. For example, like that's the right side examples model failed to reconstruct the predictions compared to the ground truth labels. So here we can summarize the two challenges. The first one is that trained with this kind of imbalanced scenario, the model may generate this imbalanced performance across in the different kind of classes. And the second one is that it will be generated at a very high computational cost because in the medical imaging, they are hundreds or thousands larger than the neutral images. So how we can address this kind of the problems? So maybe we can look at the problem from the different kind of angles. So because the machine learning model is kind of like the statistical models, in the statistical practice, sampling rows is a good way to address this kind of the class imbalance problems. So for example, here we want to detect different kind of the anatomical organs in the CT images. So in this context, different regions we are marking the different kind of colors. And for example, we want to learn a classifier in the imbalance situation. Let's say the network will get zero training errors on the training set. So the problem here about this kind of the classifier will have a lot of the wiggle room which we are trying to move around, we can see a lot of additional error around the classifier, which indicates the decision boundaries for the classifier might not be accurate enough. Alternatively, if we are trying to learn the classifier in a more balanced sampling rows, so if suppose we are trying to sample the equal number of voxel-wise features from different kind of classes, so somehow it will be work better compared to the province one. So by doing so, we can window this kind of classifier again. There are much less around the classifier, which indicates the decision boundaries and will be more accurate compared to the province one. So here we can formulate the problem, how we can efficiently to learn the balanced representation across in the unlabeled medical data. So in spite of this, we are trying to learn the balanced representation across in the different kind of classes by the sampling rows. So how we can formulate this kind of problem? So basically we are trying to assume all the data points are coming from the set of the predefined classes here that we actually care about. And our goal is trying to learn the high performance across in the different kind of class distribution. And trying to address this kind of problem, we are introducing the additional annotation or the additional structure in the form of an annotation C here on the training set, and the test time will be still the same. And the model is only get to see the input X, and the follow up the annotation will be trying to optimizing the balance classes loss. Actually, is in terms like the trying to calculate the average loss across each balance classes. So in the following, we need to think about how we can draw this kind of the equivalent sample size from the each classes. And also we want to make sure that it can be adaptively sampling because we want to incorporate it into the training process. So in spite of this, we are trying to explore different kind of the sampling roles to trying to achieve our goals. So the first one is we straightforward way to do this is trying to using the random sample with the but we sample the equal number equal sample size across in each classes during the training process, and empirically shows good performance. But somehow we still find out that the naive sampling will incur a lot of the high training variance and fail to identify some semantically hard voxels. So here are the examples that we plot the voxel-wise loss landscape with respect to the different kind of the benchmark datasets. So as the arrow point that we can see the plateau regions of the loss landscape, which marked in the green, will be indicates that the boundary regions actually yields a high loss value here. So here the two takeaway message is that this indicates this kind of the boundary regions of the plateau regions is actually suffers a high training variance. The second one is the same anatomical region should be clustering into the same certain grid instead of the all grids. So motivated by this, we incorporating the variance reduction sampling rules called the stratified group sampling and stratified standard group sampling. Empirically and theoretically, we prove this kind of the model can generate the high reliable abilities and the label efficiency for the different kind of the segmentation tasks. Here, the basic idea is kind of like we first partition the image into different kind of grids, and we sample within the each grade during the each iteration is kind of like adaptive ways. So, like the scientists and functions, the stratified group sampling is also a classical idea which around the optimization and operation research. So by doing so, we can try to adaptively sample the equal number of voxelized features from the different kind of classes and enable the model can enjoy some benefits here, and such as sample efficient, reduced variance, faster training convergence, and anchored with theoretical groundings. So here we can talk about how we can adaptively sample the or select the voxel-wise feature during each iterations of the entire training process. So the first one, we need to identify the importance values across in all the voxels. They are based on the function marking the green color here. And then we need to sample the different types of the voxel-wise feature based on the confidence map for the contrasted training objective. So here the easy voxels and hard voxels were coming from the semantic easy voxel and hard confusing voxels within the certain classes. The remaining samples were coming from the other classes here. And then we are trying to incorporating the three types of the box-wise samples into the contrastive training pipelines. And the basic idea here is we are trying to pose the positive hard voxels as close to the easy voxels because they are coming from the same classes, and push away the negative samples which are coming from the other classes here. So here we can compare to our proposed method with standard training pipelines under the 1% label ratio here. So here we just show the three examples. We actually validate on the 15 benchmark data sets. Here we compare to the standard training pipelines so the first one is we are trying to compare the accuracy on the minority classes because this is actually the important regions that we actually care about. So we can see that our proposed method can improving the segmentation quality of the minority classes with very limited label cost. And further, to explicitly account for the different kind of groups, we can see that our proposed method can consistently improving the average segmentation cost. We can say that we almost eliminate the disparities between the different groups, at least on this kind of the three data sets. So visually, we can see that our proposed method can generate the more accurate boundaries. For example, like the edge and boundary regions compared to of the different kind of the anatomical region will be more pronounced compared to other standard benchmark data, standard sorting methods. And also, comparing our series, we can say that our proposed method can generate the faster training convergence. And we can see that our sampling row can generate more stable performance with very small standard deviation, which can be viewed as the benefits of the variance reductions compounding our series. So to train this kind of model become more reliable and efficient in the insufficient label scenario is kind of our key idea to enable a lot of explorations. So let me wrap up this kind of sections. We are trying to enable the model to adaptively focus on the useful regions like the underlying anatomical features. And also we are trying to perform well on the label medical data with the imbalanced color distribution, and also trying to develop more generalized methods to optimizing for the real diseases or the small medical data sets with unseen diseases. So overall, this kind of work is kind of the first work to show the segmentation case in the medical domains using the voxel-wise sampling rules. So right now it's very popular in the biomedical domain. So they can be using for the drug discoveries or the other kind of the biomedical applications. All right, so we already talked about how we can address this kind of the class imbalance distribution, distribution problems. So in the following, I'm going to talk about more broader questions. how we can addressing the distribution share problems in the medical imaging analysis. Given the complexity of their diverse biomedical data, we realize the challenge is not only to develop some method to generalizing different kind of the data distribution, we also quite struggle to find the real-world benchmark data sets as well. So in the following, we can see that that diversity of biomedical data is very evident. So we can see that also I'm trying to give you guys some modality distribution analysis on the right now on public available benchmark data sets. We're quite worried about the success of the benchmark data sets will be rarely transferred to the real world biomedical applications because it's a really hard problem to answer because there are so many disease types in the real clinical world. So here we can see the problem is kind of like there are so many imaging modalities and the different kind of the anatomical regions. The shift problem is everywhere in the clinical deployment. And the big challenge here is that this kind of shift problems is understudied in the machine learning research. So in the recent years, they have several attempts in the computer vision domains. They are trying to building some world models or foundation models, trying to building the vision, like the segment analysis models from the Metafile labs. So the first one, we are trying to validate the performance of this kind of the vision foundation models from the Metafile labs on the medical domains. So here are some case studies that this SAM models, we can see that out of distribution performance on their tumor data, we can see a significantly performance gap compared to the fully specified, fully supervised UNet models. So here are the questions that we are quite interested about is how well the model can generalizing across in their diverse biomedical data. So to answer this kind of questions, I'm going to talk about our MESAM project. So we assembled a team to develop this kind of the generalizing foundation models. So they have two steps. The first step is we are trying to building the vision foundation models. We trying to construct the benchmark datasets. We organizing the fully super open source and comprehensive benchmark datasets, including the 84 datasets across in the different kind of the diverse tasks and modalities. And we occurred at that and standardizing them into the way that we can reflect the real clinical situation. This will come with a structure in the form of multiple medical data, trying to make the problem more tractable. Here's some examples we are trying to show here from our benchmark datasets. And then we are trying to train our foundation models on our benchmark dataset. We're using a similar architecture from the same models, and then we additionally incorporating some text embedding to add the model functionalities. So here's some empirical results. So there we validated a lot of the benchmark data sets, and all we can see some performance gap compared to the fully supervised UNet here. So one kind of note here is that the UNet model need to retraining every time on each benchmark data sets, and our foundation model do not require training. They can be directly deploying to the different kind of the clinical scenario. So we're also working on some our method to the 3D sensor for enable the interactive segmentations, and also we are trying to deploy our models to the different kind of the different kind of the clinical hospital for the daily use. But once we are trying to deploy this kind of the foundation models, we can see some promising results, but we still see some failure cases. They commonly will fail to some real diseases or the small medical data sets with unknown domains. So the reason is pretty simple is because the training distribution may not be perfectly aligned with the test distributions. So somehow the foundation model may struggle about these kind of things. So also we can look at there some existing training paradigms that on the left is kind of like the standard training pipelines, AI models. For example, we want to design the new architectures or the fine-tuning the set models. And then all of them requires the high quality manual labels. And so in the follow-up work, we are trying to rethinking this kind of problems. Can this kind of the anatomical structure have been already present in the images can help us to refining these kind of the predictions. So this is kind of the work we are trying to think about is that we really building the improving the foundation model zero shot abilities without using any high quality manual labels without the trainings. They can be directly deploying into the different kind of the scenario. So I'm going to talk about our Spruce project. So is there so here we can using the some staining contrast, we can first identify some high confidence regions that can be corresponding to the nuclear and foreground and background. So from this kind of region, we can compute the representative future prototype, and we can using the instead of using this kind of internal labels, each images can provide its internal reference because the computed prototypes can be served as the image specific anchors. And then the second step is we can try to address the uncertainties. So after obtaining this kind of the representative prototype, we need to determine whether the image regions can be assigned to them. So some of the region may be unclear, some boundary regions may be, some of the region may be clear, but some of the boundary regions may not be very clear. So we don't want to enforcing all the pixels while be making the decisions. So motivated by this, we can using the partial matching schemes, we can assign the most of the confidence regions first and leave the uncertain regions unassigned. And then we can gradually including more regions, the segmentation may become more reliable and stable. And then we can recover some clean foreground mask without over-committing some noisy boundary pixels or voxels. So finally, we can convert this kind of the stable region into the point prompts, and the structure-derived prompt will be guide the foundation models, the set models, and this kind of prompt can come directly coming from the image structure without require any manual labels, which will be deliver us a very clear instance mask in a fully training free pipelines. So here's some takeaway message. We can see a very robust zero-shot generalization abilities across in the different kind of the benchmark data set. And also the second one is that our method is can be deployed into is a plug and play modules. They can be compatible with different kind of the different types of the foundation models to enable more segmentation performance. Okay, so so let me quickly wrap up this kind of the third section. We are quite fortunate that our work got a lot of visibility. For example, like our MathSam papers was highlighting the Nature Communications as the editor highlight webpage. And also this year, we are trying to organizing several workshops. Um, so we also see a lot of the early adoptions in our medicine work into the research and clinical settings. And right now, the community around the foundation models is still growing up. We are quite optimistic about the future progress here. So, all right. So let me quickly sum up these sections. Is we are starting with to develop some generalizing method like the contrast learning to find the right identifiers from the imperfect medical data. And then we are trying to using some adaptive sampling rule to learn the best representation, which involves some rigorous and classical statistical tool to push towards the segmentation robustness and the label efficiency. And further, we are trying to talk about how we can dive into the challenge of the diverse biomedical data in the real clinical situations. So reflecting to my research goal is trying to develop a reliable, efficient, and a general method for the biomedical machine learning system that can anchor to the real-world applications. So in the end, I would like to end with a few minutes to talk about my currently research agenda. I really believe that we are in a very unique and exciting time in the biomedical domain, and also it's very important to make a big bit in the futures. So beyond the talk, I'm going to cover some currently project my group are exploring. So the first directions is we are thinking about because we do not have the enough high quality labels, so we are trying to using some generative modeling to help the biomedicine consider because we don't have the same data skills as a general machine learning task. So more broadly, This kind of generative AI method can enable some discoveries, improving the robustness, and enrich some biomedical data. So in the following, I'm going to sharing with you guys how we can build on these kind of the directions. So the first project is the city enhancement project. So the idea here is trying to recover the high quality city distributions from the corrupted measurement. Actually, we are trying to using some generative modeling approach to train the city foundation models on the very large physics-driven simulations of the non-ideal city images, which can be the resulting models can be general consistently across in the 27 downstream enhancement task, improving the existing task-specific method. And the second application is that we are trying to working on some generative modeling for the EEG signal, because the EEG signal is very hard to collect, and we actually do not have enough EEG signals in the real world collections. So here are some examples. We can simulate some, generate some real the real EEG signal across in the different kind of the clinical categories, because our method can continuously learn these kinds of projections instead of the discrete learn these kinds of temporal features. So in the background, for example, like in the background and the eye movement patterns, we can see the very stable the activities, and also they can be captured some background activities and the non-stationary clinical patterns for the they can be work very well across in the multiple different kind of the downstream task classification task. And then the second direction is that we are also trying to explore the different kind of structure among the different kind of the biomedical data to help the model become more generalizing across in the diverse biomedical data. So here is the kind of the work. The information is kind of like coming from the metadata. For example, they can be allow us to inject the different kind of the biomedical knowledge as a right in database to the problems. And for example, that we are trying to learn the models that they can be invariant across in different kind of dimension because they have different kind of the correlations with each other. On the other hand, we can somehow using kind of their this kind of information coming from the doctor explanations because they are very rich text data in the hospitals. For example, we can using some language models to learn this kind of the clinical notes or the doctor explanations, and then using this kind of language model to steal the underlying or the latent representation to make the model become more robust to the different kind of the biomedical domains. And this kind of the metadata or the explanations are widely available in the hospital. So somehow we are trying to and using this kind of the arbitrary data to train the model become more robust. So current state or the current state training pipelines or the models is kind of like the throughout of them away. So actually we can trying to leverage this kind of the rich text data in the hospital to train the model become more reliable and robust. And the third direction is that actually we are trying to think about is become more trustworthy and reliable biomedical system. So because actually we want to achieve the joint performance across in the doctors with the doctors. So different from the standard training pipelines, we are trying to optimizing the model alone. We actually require the shared understanding from both sides. So actually here we are trying to provide some hooks to enable the more clinical or to enable more effective real-world clinical interactions. So one experiment we are trying to show here is that the model may launch on the sparse correlations to making the model become unreliable because that we are trying we find out that the model may trying to learn the most frequently shortcut instead of the core features that we actually care about. So the cost here is trying to classify whether the patient in the X-rays is illness or non-illness. So we're trying to train the machine learning algorithm on the chessboard benchmark dataset, and then we find out the imbalanced group is become to the or the subpopulation groups is coming from the male patient and the female patient. So we find out that the model is trying to learn to classify the illness instead of trying to classify so instead of classify the illness, the model is trying to theorize to classify the genders. So the model may work well on all the majority male patients against the illness because the majority data points is coming from the male patient. And somehow the model may not learn the right things because these kind of the correlations may not be always hold up. Somehow when we are trying to diagnose the female patients, the algorithm may fail, so this indicates the misleading heuristic may not work well all the time. So one of the work is one of the direction we are trying to work is trying to improving this kind of the robustness against the subpopulation shift problems. And also we are trying to incorporating some theoretical and statistical guarantees into the medical AI system because we are trying to think about we need to provide the doctor with this kind of a tool to understand root cause and modify and interact with our system. This can be we can make the machine learning system more reliable, especially because we are trying to because thinking about the clinical environment is keeping changing. We are trying to combine the adaptabilities of the doctors and the statistical abilities of the machine learning model. We can enable more intelligent clinical decision making. So, all right. So during today's talk, we talk about the model may suffer some risks like some unreliabilities or less robust in some of this kind of the scenario. And also we see a lot of the failure examples across in the different kind of the applications. So on the other hand, on one hand, it's very urgent and serious problems because this kind of model are already out there. We need a better solutions. So on the other hand, from the more optimistic views, they have a lot of the potential that we can building these kind of the machine learning models to help us the more important biomedical application like the diagnosis or treatment. So I really hope through my research to building the model become more robust against the challenge scenario and they can be more reliable and interactive more effectively with the real clinical work. So here's some of my collaborator and the students from the engineering schools and the medical schools. So without them, a lot of project will not be any successful. So thank you for having me here. I'm very too happy to take any questions.
Wonderful. Thank you so much for that fantastic talk. You covered a lot of ground. So the question and answer box is opened. If you have any questions, please feel free to post them there. Perhaps I would start with one first question. You talked a lot about training with imperfect data and how we can still leverage this imperfect data. But to what extent do you think in the years to come, as AI systems become more normal in clinical practice, to what extent do you think methods will be used to leverage such imperfect data? And to what extent do we have to make sure that the data is good quality, or we could improve the acquisition of the data?
Very great question. So, actually, I think we need to do both of them. The data uncertainty is actually coming from the acquisitions, like also have the high variabilities across in the different kind of the imaging scanner, and also different kind of the dose levels. So they have a big variabilities according to their data internal self. And also they have their big variability of the imbalance problems in the disease regions, especially because thinking about the lesion or tumor regions compared to the background regions. Actually, the background regions always have the higher portions. So I cannot see 100% of the 95 or 99% the tumors of the disease region will generate the will have the smaller portion of this kind of thing. And also also the diseases will be happens in the different kind of the subpopulation groups. For example, like clearly is kind of like the gender as race and a kind of the other different kind of the attribute will be causes kind of the imbalance imbalance groups. So all of them um, uh, be influence the model to make the inaccurate corrections or predictions. So and also even the manual label data will have their um, high uncertainties. So at this point we use some um, like the uncertainty corrections or calibration method to help us to address internal label annotation noise. So all of them are very important for the currently stage of the machine learning system or models kind of things. And one of the direction I'm thinking about is maybe we can using some generative model to generate the different simulate this kind of the data under the different kind of the situations. So which means we can augment or potentially we can augment this kind of the um, imbalance groups order to improving this kind of types of the accuracy or robustness across in this kind of the small portions of groups.
Yeah, yeah, makes a lot of sense. We could use synthetic data for that. So for the next question, that is from Alex Bauman, thanks for the talk. How reliable can synthetic data be generated with small ground truth data sets, and how can we improve it further?
It's very great questions. Actually, we are actually we are still this is an ongoing project. We actually work with my students right now, and um, I can so actually, we are trying to simulate this kind of so let me give you guys some examples. So this examples is like we are trying to address the low-dose CT's enhancement problems. Actually, we can from the CT physics. Actually, we can try to simulate the projection views and also those levels under different kind of situations. We actually do not require the prior CT information. We just using we just can be plugging different kind of the parameter to simulate the CT images under different kind of circumstances, and then we can simulate the infinite data skills, and then we can train the foundation models on these kind of skills, and so we can somehow address this kind of problem. And because we can address the problems, another reason is because we have we actually have um, we can simulate this kind of the circumstances, but especially for the compared to the EEG data, it's hard to simulate because we actually do not know anything about the very detailed information about the EEG signals. And also currently we are trying to building some BCI applications with a very famous company in United States. But somehow we still have the challenge to collect this kind of the EEG signals. Uh, and how to try to simulate this kind of one. So currently we can only show some uh, uh, promising preliminary results on the 21 data downstream task, but somehow we cannot say there we can directly to simulate the high quality patterns from the very small data set. We need to pre-train the model on a very large portions of the corpus, EEG corpus, and then we can try to simulate this kind of data.
Yeah, makes sense. Great. So moving on to the next question. Thank you very much for the excellent talk. As there is a push towards different techniques to compensate data variability and missing data from different reports, should there be an equal emphasis in increasing AI literacy with healthcare professionals to help reduce this?
I think it's a very promising direction to incorporating this kind of the medical literature and the corporate the tech corpus to the trainings, and also uh, like the 2 weeks ago, the Stanford researcher they published a paper that they show that if we can only using uh, uh, the text data, only using the text data can also generate this kind of the high quality prediction accuracy. I think it's reasonable somehow there. I think there because the text data always have some moderate supervision coming from the human brains. Actually, this kind of data is more more accurate. The supervision with the underlying supervision, this kind of data is organizing more accurate. The image data, the challenge for the image data is because the image data is high dimensional, so it's hard to get there because there are so many redundant noise during the images. So it's hard to formulate a very high quality latent vector using uh, different kind of AI models. So maybe we need to think about to optimizing this kind of the image encoder architecture to get their better uh, to get a better latent vector to more work more compatible with the text part.
Makes sense. You also talked about interaction between the clinician and the AI model. So, how do you believe is the best way to do this, to build models that integrate well into clinical practice and that the physician can interact with?
I think it's a very great question. So, uh, right now, one of the work is we are trying to working on called the foundation models. Is there what foundation models is actually we are providing some interactive pipelines of platform with the doctor, so they can be like the ChatGPT or the cloud platform. We can just input some text information or the image information, and the doctor can interact with this kind of the platform, and they can provide some feedback to improving this kind of the models, and the model can be quickly to update their model with. But right now, we just work on a very small clinical site internal for our use. We don't extend to the other kind of the hospital. So in the future, we are trying to think about to collaborating with more clinical sites.
Great. Okay, excited to see that work then. There are no more questions right now, and we are almost at the hour. So I would thank you again so much for the fantastic talk. Kai, would you like to add something?
Yeah, thank you so much, Chenyu, for the fantastic talk. And I think this is perfect conclusion of our spring 2026 IEEE MBS webinar. And hope to see everybody in the fall semester. Thanks, everybody.
Thank you,
Thank you
everybody.
for having me.
Thank you for coming. And we will make this talk also available in our YouTube channel, like all of the other webinars.
Okay. Thank you for having me
Yes.
here.
All right. Take care. Thank you.